Hi folks, this is Dr. Khaleel Khan welcoming you to GFG platform. And in continuation of our operating system academic series, today we are going to look into lecture number 8. And we are basically dealing with the topic of CPU scheduling. So in earlier videos, we have seen the fundamental CPU scheduling techniques like first come first serve, shortest job first, shortest remaining time first. So boys and girls, today we are going to look into another important scheduling technique as far as time sharing systems are concerned and multi-programmed operating systems are concerned. So one of the important scheduling technique there is called round robin. So very important scheduling technique, whether it is for your university exams or perhaps for competitive exams. Essentially you can expect a lot of questions, a lot of problems on round robin. So this is as usual the disclaimer about the content that we are going to use from the textbook of Galvin, as I mentioned earlier. And so essentially we start our discussion with this scheduling mechanism, scheduling technique, which is called round robin, as I mentioned. So this is basically used in, so let me write here. So to add that, I just want to mention that this is used in preemptive based, is one of the preemptive technique like SRTM, preemptive based multi-programmed operating system. And preemption is based on time quantum. Essentially, I will not be wrong if I say it is used in time sharing systems, interactive time sharing systems. Okay. And to add on, the initial versions of Unix operating system used to basically this scheduling mechanism by name round robin. The Unix used to use it, the round robin technique. So as far as the selection criteria is concerned and the mode of operation, selection criteria, the parameter based on which the selection of the process is done is arrival time. And if you remember and recollect, arrival time was the metric, was the parameter that we have even used for first come first serve. But first come first serve was essentially non-preemptive, and this is preemptive. And therefore preemption is based on a philosophy, based on a parameter called time quantum, also called time slice. We'll write time quantum in short as TQ, and is also called time slice. So I'll tell you the background behind this time quantum and the essential working principle of this algorithm also we'll see. The mode of operation of the scheduling technique, mode of operation, in what mode it operates. I mean to say, does it operate in preemptive mode or non-preemptive mode? So essentially this operates in preemptive mode, preemptive in nature. And sometime, because the selection initially is based on arrival time, so quite possible that sometimes I may have multiple processes having the same arrival time. So just in case, imagine if we have any conflict with respect to arrival time, conflict with respect to arrival time, we will resolve it in favor of lower process ID. I mean to say that if there are multiple processes present in the queue with the same arrival time, then who is going to be taken up first? The one which is having the lower process ID. So that's what I'm saying. So here I would like to make a statement before I take up the numericals to make you understand the ideology. Preemption of the schedule process, preemption of running process. The main working core principle of this algorithm I'm writing in the form of a statement. Preemption of running process is based on the expiration. What is the meaning of expiration? Expiration means completion. based on expiration or completion of time quantum. Based on expiration or completion of time quantum. So this is the nutshell, or you can say the precise summary of round robin, the working of round robin. So let me elaborate this, what does this mean and how step by step the algorithm of round robin works. So boys and girls, as we say, the ready queue is maintained in the form of FIFO queue. That means the processes are added in the queue based on first come first serve order, first in first out order. So ready queue is essentially FIFO queue. So let me write here. The ready queue is a FIFO queue. The processes are added based on the FIFO order. So that means when the time comes to make a schedule of the process, to schedule dispatch a process, the one who is at the front of the queue will be taken and dispatched on the CPU, like first come first serve. But the essential difference between the round robin and first come first serve is that first come first serve is non-preemptive and this is preemptive. So preemption is based on time quantum. So that what will the operating system do is that to the allocated process, the process which has been scheduled onto CPU, the operating system will give it time quantum, a fixed time duration, time quantum, like 10 seconds, for example. So the operating system is telling the process that you are given 10 seconds. If you complete within 10 seconds, well and good, you will leave the CPU, just like in first come first serve. Or within 10 seconds, if you need any IO, if you need to execute any system call or any resource request is to be made by the process, then the process voluntarily will release the CPU. So within the time quantum, if the process complete, well and good, it will leave. Within the time quantum, if it needs IO, well and good, it will leave. But just in case if the process neither complete nor require IO nor go for any system call within the allotted time quantum, then come the concept of preemption. So the operating system will tell the process, boss, I'm sorry, your time is up, you have to leave the CPU. Why? Because I want to give the chance to other process. There are other processes waiting. I don't want them to get suffered from the problem of like lack of interaction or responsiveness or starvation. The basic objective of round robin scheduler is to make the system responsive, interactive scheduling. That's why it is also called interactive scheduling. So within the allotted time, well and good if it leave, right, when it complete or go for IO. But in case if the process doesn't complete within allotted time, in case within allotted time if it does not go for IO, then comes the role of operating system, causing the process to get preempted from CPU. And then the preempted process will be added back to the queue because it's a FIFO queue. And the whichever process next in line in the ready queue will, in the FIFO order, will be allocated to the CPU. So this is the philosophy. So first P1 may run, then P2, then P3, then P4. In round robin fashion, again P1, then again P2, then again P3, then P4 with time quantums as the maximum time for which the process can run. So this is the basic notion or the ideology of round robin. And the main intent, the main objective, as I said, is to improve interactiveness, to bring responsiveness within the system. This is the basic ideology of round robin. So let's try to make an understanding, or let's read some points here if you for your notes perhaps. Each process gets a small unit of CPU time, that is called time quantum, usually like 10 to 100 milliseconds. Those are the practical values. After this time has elapsed, boys and girls, I want to draw your attention. After this time has been completed, expired, elapsed, the process is preempted and added to the end of the queue. This is what I want you to firmly understand. Preempted process will be added to the end of the ready queue, so that we always maintain the FIFO concept. If there are n processes in the ready queue and the time quantum is q, then each process is guaranteed to get 1 by nth of the CPU time in chunks of at most q time, t units, 1 by nth of the CPU time. No process will wait for more than n minus 1 into q time units. That's the maximum time the process will have to wait. So it all depends how much the process is waiting based on the number of value of n and q. If there are more processes, time quantum is more, the process will wait more. If there are less number of processes and time quantum is also less, then the process will wait for less amount of time. So timer interrupts every quantum to schedule the next process, right? Performance, of course, we'll see after some time. I would like to basically work out some numericals for you so that you can have clarity of understanding. So boys and girls, I will take the first example. Imagine for instance the following data. Initially, if I just give you process number and burst time, these are regular data sets. Sometime if you see the textbook of Galvin, they will give the data set directly like this, say 4, 5, 3 and 2. And let's imagine the value of time quantum is 2 units. These are time quantum. I would like to show you here in this problem that there is no mention of the arrival time. So as I said earlier also perhaps that if in case in the data set, if there is no mention of the arrival time, then it means by default the arrival time is assumed to be 0 for all the processes. That's the default objective you can follow. In case if arrival times is not given, then you can imagine all arrival times to be 0. That means you are considering that all the processes have arrived at the same time. So the arrival time is 0. Okay, remember this. Just in case in the exam also, your university exam generally, or maybe any competitive exam like GATE or ISRO or P or any other such competitive exam, just in case if you are getting any question where there is no mention of the arrival time, then remember by default arrival time is assumed to be 0. That's why I am taking this problem first. So boys and girls, when there is a conflict, because all arrival times are 0, so that means the ready queue will have to maintain the order of lower process ID. So first I will add P1, then P2, then P3, then P4. And I would also like to make a mention that for simulating the trace of round robin, it is highly important you basically maintain the ready queue, because without ready queue, it's difficult essentially to show the order in which the processes get run onto CPU. So time always starts at 0 and moves in forward direction, as I have been emphasizing. So at 0, it is very clear that there are 4 processes. Who is at the front of the queue? P1. So P1 will take the charge. P1 need 4 units, but allotted time quantum, as I said, is 2 units. So P1 will run for 2 units of time. It gets preempted and then added back to the queue, P1. Then P2 take the charge next. It is also going to run for 2 units, 4. So P2 get preempted and put back to the queue. Next to run is P3. P3 need 3 units, so it run for 2 units, 6, get preempted and put back to the queue. Next P4 take the charge. Boys and girls, please observe, P4 need 2 units and time quantum is also 2 units. So P4 will complete at time 8. P4 is over. Then I don't need to add P4 back to the queue, is it not? Then who is at the front of the queue? P1. So P1 will take the charge. P1 need another 2 units, so it's going to complete at time 10. Then P2 will take the charge. P2 will run for the second round 2 units, so 12 will get preempted, added back to the queue. Because the total burst time of P2 is 5, so P2 has run for 2 plus 2, 4 units. Is it not? 2 plus 2, 4 units. So 1 more unit is pending for it, so that's why we have added back. Then P3 will take the charge. P3 need 1 unit to complete, completes at time 13. Then finally P2 runs. So P2 also need 1 unit of time. It also completes at time 14. So as usual, as we have seen earlier, you can compute the turnaround times, waiting times of the processes, and also the average turnaround time, average waiting time, and thereby you can basically make a full computation of all metrics. And for example, if you want to calculate the schedule length here is 14 minus 0, so 14. This is the ideology of basic issue of round robin. We can take some variation where I have assumed, for example, different arrival times. Say, for example, I have a data set like process number, arrival time, and burst time. Different arrival times may be given. Again, you can imagine 4 processes, right? And the arrival times are something like this, 0, 3, and then next to arrive is 1. Okay, and these 4, and next to arrive is 2, and these take time 5, and next to arrive is at time 4, for example, and let's say it take time 6, something like this. And here I can take same time quantum 2 units, or maybe a different time quantum. Maybe I'll work out with 2 itself, and you can prepare the GAN chart and also show the ready queue contents. All right. So this is ready queue, imagine, and this is the CPU. So please, I want you to have a close look at the working of this problem as well. Okay, time moves in forward direction. So boys and girls, as you see here, be careful, at time 0 I have only P1. So P1 is going to start on CPU. Allotted time quantum is 2 and this runs for 2 units, so therefore 2. Its balance is 1. So P1, and now observe, this is very, very important, boys and girls. So between 0 to 2, if you observe the data set, 2 and 3 are coming, right? P2 has already come, so I add P2 in the queue. At time 2, there is a tie now. Look at this, there is a tie now, P1 and P3, P1 and P3. So P1 is trying to go into ready queue, P3 is also going to come into the ready queue. So here comes the conflict. So who should be given the access first? Should I add P1 first or should I add P3 first? So, I mean, if you go with lower process ID, then P1 should be added. Some authors I have seen they will add P1 first because it has come first, right? It has lower process ID. But I prefer to add P3 for the reason that I want to make the system more interactive. I want less waiting times, right? Less response times. So in that scenario, because my objective is to improve, so here I'm going to write that statement. The objective is to minimize average response time, right? Then in that case, new process should be added first. This is a very important point to understand. So I'm going to favor the new process. Why? I want to make the system more interactive. I want to have less average waiting time, right? Response time. So boys and girls, here in that sense, I'm going to add P3 first and then followed by P3, P1. Do remember that the other process P4 has not yet come. Only this is the scenario. So be careful, P4 will be added not now, later point of time when the time becomes 4. So meanwhile, P2 take the charge. Observe P2. It runs for 2 units, 4. Its balance is 2. And now P2 will get preempted, getting added to the queue. Again, the same philosophy. At time 4, P2 is contending to enter into ready queue, and at the same time P4 is also trying to enter. So we said we are going to favor the new process. So we add P4 and then P2. The point. So as I repeatedly saying, in some cases the authors will add P2 then P4, but I follow this approach. Why? To minimize the average response time. This will minimize because already P2 has got a chance to run for 2 units. So we will give the chance to the new process. That is the basic ideology. Okay. So generally in such cases, what happens is in the question they will mention how to work out. Don't worry about it. In the competitive exams or university exams, these conflict resolutions, if you see the textbook, there is no hard and fast rule. Generally, it is not mentioned in the textbooks. So what I presume is that in the question, the examiner should specify how the contention should be resolved. What is the aspect that you are trying to minimize or maximize, and based on that you can do it. So boys and girls, next to run is P3. P3 will take the charge. So P4 then P2 we have already added. P3 is going to run for the first time till 6. P3 has a burst time of 5, so it gets preempted and we add P3 back to the queue. Then P1 is going to take the charge. P1 has a balance of 1 unit complete at time 7, followed by P4. P4 is running for the first time, right? P4 is running for the first time, so therefore it gets preempted at 9 and get added to the queue. Next to take the charge is P2. P2 earlier ran for 1 burst, 2 units, another burst, total completing at time 11. Then P3 take the charge. P3 will run for the next time, right? Second round, first round, second round, 13. Then we add P3 again. Then P4 is going to run second round, right? So we are going to get preempted at time 15. So P4 will get added again. So don't forget to add the processes because they have not yet completed. Every process should complete the total burst. So what happens? Next P3 is going to run. P3 has already run for 4 units. Its balance is 1. So P3 is going to complete at time 16, followed by last P4. P4 has already run 2 bursts, 2 rounds, 2 plus 2. So its balance is 2. So it completes at time 18. So now if you want, you can calculate the average turnaround time, average waiting time, average response time. But however, I just wanted to show you what is the average response time. Average response time. Okay, so check it. Response time of a process is defined as the time of its arrival to the time at which it get onto CPU for the first time. Right? First waiting time is response time of the process. Like P1 came at time 0, got scheduled at 0. So essentially its response time is 0 plus P1. Look at this. P2. P2 came at time 1. It got scheduled at time 2. So it waited from 1 to 2, 1 unit. So its response time of P2 is 1. P3. P3 came at time 2. Look at this. P3 came at time 2. It got scheduled at time for the first time at time 4. So 2 to 4 it waited 2 units. So 2 units. Plus. Then P4. Look at this. P4 came at time 4 and got scheduled at time 7. 4 to 7 it waited 3 units. So 3 units. Right? Divided by 4 processes. So 3 plus 3 is 6 by 4. Right? 6 by 4 happens to be how much? 2 3 are 6, 2 2 are 4, 3 by 2 means 1.5. The average response time is 1.5. Boys and girls, as a matter of comparison, what you can do is, following this paradigm, the response time is coming out to be 1.5, average response time. You can do the other way if you want and check. That means instead of adding P1 first, if instead of adding P3 first, the new process at time 2, if you would have added P1 and then P3, and if you follow that paradigm of lower process ID getting added first, you would see that the average response time will be higher than 1.5. You can cross check, and in the comment section you can report to me your confirmation. Okay, you can do that and check that if you favor the lower process ID rather than giving the chance to the new process, the average waiting time will be more than 1.5. So this approach will reduce the average response time, and you can also verify that average response time will be different from average waiting time. Both are different. For preemptive schedulers, for non-preemptive schedulers it will be same. For preemptive schedulers this will be basically more, response time will be more. Right? Sorry, response time and waiting time will be different. Third example, I can even have the data set with IO burst time. You can even work out round robin with IO burst times. Like for example, I take a simple data set where I have process number, arrival time, and I can have a series of burst time, then again IO burst time, then again burst time. If I have a data set something like this, okay, this is the life cycle of the process. This implies that the process is initially spending some time on computation, and then the process may go for IO and spend some time on input-output operation, and followed by IO operation. Again, the process may run for certain amount of time on CPU and complete. So here, inherently, we are assuming that the process will complete from running state. The process won't complete from, will not go to terminated state from block state or ready state, only from running state. Okay, that's our inherent assumption. So let's take an example of 3 processes and prepare the GAN chart for this. The arrival time, initially it spent time of 4 units, and here it spent time of 10 units, and again 2 units to complete. Next process comes at time, for example, 1, okay, and this spent of time of 2 units and 3 units and 1 unit. And next come process 2, spend time of 1 unit, spend time of 5 units, and spend time of 3 units, something like this. This is my data set. And for example, if I use time quantum is equal to 2 units again, then how are we going to work out, prepare the GAN chart for this type of data set? Okay, so that will be an interesting aspect. I would like you to have a close look at this. So again, as usual, this is our ready queue, and let's say this is the state of CPU, right? So this is the CPU and this is the ready queue. So at time 0, we could see we have P1. So P1 is going to start the execution with a time quantum of 2 units. So between 0 to 2, already the processes have come in the order P2 followed by P3. P3 has also come. Or if you just want to slightly vary the data set, let's imagine P3 has not come. I'll put this value 3. So in that situation, we'll assume only P2 has come at time 1 and at time 2, P3 has not come. So we are going to add P1 again. The point of understanding. We are going to add P1 again. Then who is going to run? P2 is going to run. P2 run for 2 units. And after that, it doesn't get preempted. It will go for IO. You look at this. After completing 2 units, it is going to start its IO. Who? P2. P2 is going to start its IO. For how long? 3 units. Starting from 3 units means it is going to finish its IO. It's going to finish its IO. Here I will say. It's going to finish its IO at time 7. 4 plus 3. IO is going on. Now, why between 2 and 4 you should monitor that already in the ready queue we have received P3 now. P3 has come when the time was 3 here. When the time was 3, P3 has joined the queue. So don't forget about this concurrency. Then P1 is going to run on CPU again. P1 has earlier run for 2 units, now another 2 units, 4, 6. So at this time, P1 has completed all its 4 units of burst time. So now the time for P1 is to go for IO, concurrently IO. We assume we have multiple IO devices so that both the processes can perform their IO operations. So P1 starts its IO operation and need a total of 10 units. Look at this, 10 units. So starting at 10 units means P1 is going to complete its IO at time, for example, 10 plus 6, 16. Boys and girls, I hope you are able to understand the working of this problem. Round robin with IO burst times. Then essentially in the ready queue I have P3, but here I would like to also observe. Now observe. P2 is going to finish its IO at time 7. Observe it. So P3 is going to take the charge on CPU. P3 need 1 unit of time to run 7. So boys and girls, here at time 7, P3 after completing 1 burst need 5 units of IO. Means P3 will go for IO operation now, concurrently, parallelly, along with other processes. So P3 starts its IO at time 7 for 5 units. Starting at 7, 5 units means it is going to finish at time 12. It is going to finish at time 12. The IO operation of P3 is going to finish at time 12. Am I right? Look at this. What is going to happen at time 7? Look at this. What is going to happen at time 7? At time 7, P2 is going to finish IO. So from IO, it will come back to ready queue, is it not? So we will add P2 here at time 7. Right? So P2 will immediately take the charge on CPU, and P2 in its second burst need 1 unit of time. So it runs for 1 unit, 8 it completes. P2 is over. Now when P2 is over, P1 and P3 are busy still with their IO, and P3 is going to finish IO at time 12 and P1 is going to finish at time 16. Meanwhile, ready queue is empty, the processor is bound to be idle. So it is going to be idle till what time? Till some process come back to ready queue. Who is going to come first in the ready queue? P3 is going to come. At what time? At time 12. So that means from 8 to 12, from 8 to 12, the processor is going to be idle. Is it not? Processor is going to be idle. So this is the idleness of CPU. So at time 12, P3 is going to join the ready queue, and from ready queue it will come on to CPU, and P3 needs 3 units of time. 3 units. So but it is time quantum is 2. So first it run for 1 burst, 12 to 14. At time 14 it go back to ready queue and again come because there is no other process. So P3 only will take the charge and complete at time 15. 3 units of time. So boys and girls, again observe at time 15, P3 is over, P2 is also over. P1 is still busy performing IO because P1 is going to complete its IO at time 16. So that current time is 15 now. So that means 15 to 16, again we are going to have idleness. This is a very important aspect of scheduling. Then what is going to happen? P1 is going to finish its IO at time 16, and then it will go back to ready queue, and from ready queue it will take the charge. It needs 2 units of time, so therefore it is going to finish its execution at time 18. So this is the working of round robin with input output burst times, okay, with different time quantum. And once you prepare the GAN chart, you can basically compute any metric like turnaround times or waiting times or response time, or as a matter of fact, anything can be computed. Now, taking some standard problem, this is a problem from the Galvin textbook directly, okay. So, this is the GAN chart and this is a simple data set. You can see here P1, P2, P3, P1, P2, and time quantum here is taken to be 3 units for example, right. So, the processes are completing here at 0 to 3, 3 to 6, right, and here you can say 9, something like that it goes, and after that P1 is only going to run for continuous times. Fine. Here I am going to show you the impact of time quantum and context switching time. This is a very important diagram from the Galvin textbook where it is going to demonstrate what is the impact of time quantum and the number of context switches. So imagine for example, I have some process whose burst time is 10 units. Okay. And if you take for example time quantum of 12 units, time quantum is no more than the burst time of the process. Time quantum is more than the burst time of the process. So therefore, what is going to happen? The process is going to run in one stretch, all for 10 units and complete. So therefore, it means there is no context switch. There is no context switch. Process doesn't get preempted and go back to ready queue. It all complete in one stretch, so no context switching. Number of context switches are 0. However, if you take time quantum of 6, even if I have a single process, I will have context switch. That is the point I am trying to highlight. So P1 will run for first round 6 units, go back to ready queue and again I come. So there is one context switch here. That's why I had number of context switches as 1. However, if I take time quantum of 1 unit, just 1 unit, then what is going to happen? The process will run for 1, 2, 3, so 10 bursts, one unit each. So how many context switches have happened? You can count here 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 context switches. So even if I have a single process, context switch will be considered, context switch will be accommodated, will be counted, even if I have single process. So don't think that I have single process, it will run at a stretch for 10 units when the time quantum is less than the burst time. That is the point we are trying to highlight. Next aspect, the correlation between average turnaround time and time quantum. Sometimes people may ask, what is the impact on average turnaround time with time quantum? If you take this data set, there are 4 processes. There are 4 processes and the burst times are 6, 3, 1 and 7. Okay. So point is, if you keep on increasing the time quantum, on x-axis, like when the time quantum is 1 unit, the average turnaround time happened to be 11. You can prepare the GAN chart and check. When the time quantum is 2, the turnaround time has increased to 11.5. When the time quantum is 3, check it, time quantum is 3, the average turnaround time got reduced, maybe 10.8. When the time quantum is 4, the average turnaround time again got increased, 11.5. Time quantum is 5, it further increased and then suddenly dropped. So boys and girls, I am trying to say that there is no such correlation that time quantum should increase or decrease. As you see, it's a wavery curve, like wavery, sometime increasing, sometime decreasing. So nothing like that, a proper relationship between them. But however, we say 80% of CPU bursts should be shorter than time quantum to have a better average turnaround time. So it varies with the time quantum. That is what we want to say. Okay. And by and large, if you observe what is the general performance of round robin scheduling techniques. So the performance of round robin essentially depends on the value of time quantum. So time quantum is going to define the behavior of performance of round robin scheduling. So we would say that the time quantum that you select may be either small or may be large. So we will study what is going to happen when the time quantum is small and when the time quantum is large. Okay. When the time quantum is small, then essentially it will lead to more number of context switches. More number of context switches. And here you can say when the time quantum is large, it will have less context switch overhead. less context switch overhead. Okay, but there is an advantage. So this is the disadvantage of having more number of context switches. Context switch overhead will be more when the time quantum is small, but this will make the system more interactive. This will lead the system to be more interactive, more responsive. The processes will get a chance to run on the CPU at the earliest. Here, poor interactive, poor responsive. That's a simple comparison between smaller quantum and larger quantum. But however, suppose for instance, if I say that the time quantum become very small and the time quantum become very large. So what impact is it going to create in the performance? So here I would say when the time quantum become very large. By very large, I am trying to say that maybe perhaps like one of the example that I have given you earlier, it becomes so large that it is greater than the largest burst time of the process. If the time quantum value is greater than the largest burst time of the process, then how will the processes run? It become very large, so the round robin scheduler degenerates to first come first serve. It works like first come first serve, right? Round robin scheduler will start working like first come first serve when the quantum is very large. And when the quantum is very small, look at this. When the quantum become very small, that means most of the time the processor will be busy doing context switching rather than doing useful computation, right? So in that case, we would say the efficiency of the system, useful work which is done by the processor, efficiency of the system almost tends to near becoming towards 0%. Useful work done by the CPU is approaching to 0%, maybe 5%, 3%, 2%, 10%, very, very low efficiency. Most of the time the processor will be busy doing overhead activity rather than doing useful activity. So that is the inherent performance of round robin scheduler. Okay, so this is all about the round robin. As I mentioned, this is one of the very important topic. You can expect a full-fledged 10-mark question, 5-mark question, numerical in your university exam, college exam, semester exam, and in case of GATE exam or other competitive exam also, you can expect simple numerical questions based on round robin. So I hope this lecture would definitely be of some use, right? Very helpful and beneficial for all aspects. In the next session, I will present another scheduling mechanism, which is also called priority-based scheduling. Then we can even have priority along with round robin, hybrid technique, integrated technique. So, and then finally the last scheduling technique, multi-level, will present that in the next session. Thank you so much. Take care.